We restored locomotion in primates with spinal cord injury. And for this, we developed a brain-spinal interface that decodes motor intention from brain signal, bypasses the lesion, sending this information to the spinal cord below the injury in order to reproduce the intended walking movement.
For the first time, I can imagine a patient, completely plegic, being able to obey to his brain commands through this brain-spinal interface. If you have a lesion of the spinal cord, then the command is not going to reach the legs and going to stop at the level of the spinal cord lesion, and the primate is not going to walk.
So concretely, we inserted 100 electrodes in a small region of the cortex that control the leg and send the information from all the neurons we recorded to a computer that decoded the motor intention of the primates based on this signal. This means the extension or flexion movement of the leg. And the computer sends then this information to an implantable stimulator that had the capacity to deliver stimulation at the correct location with the correct timing in order to reproduce the intended extension and flexion movement of the leg. The brain-spinal interface required the development of a fully implantable wireless real-time system that enabled the primate to behave freely without constraint. We understood how to extract the motor intention with mathematical algorithm and where and when to stimulate the spinal cord to induce the walking movement.
To make the link between the decoding of the brain and the stimulation of the spinal cord and to make this communication exist is completely new.
This is the first time that a neurotechnology restores locomotion in primates, but there are many challenges ahead, and it may take several years before this intervention can become a therapy for humans.